Welcome to another fabulous day in Calculus 3. We're continuing our trek through polar coordinates and double integrals. So last time we started polar coordinates and double integrals. So we're going to do a whole bunch more examples today, and then we'll get into mass of a planar lamina. So we left off, and this was the problem we're coming up next. Suppose that you're trying to find a volume of a solid. You want to set up a double integral in rectangular coordinates first, and then we will notice that it's kind of hard to do in rectangular, so then we'll convert. Okay, but first we'll set it up. So here's the capping surface. Z equals square root of 16 minus x squared minus y squared. And below by the circular region, that's understood to be in the xy plane. Okay, and so that's going to be looking like the base of the solid. Okay, so of course I'm out of paper, so I guess I'm going to need some more. So we know the volume is going to be a double integral over the region, and we put our capping surface in the integrand like this, and then dA. There's sort of a generic look. But then, we got the region of integration, which they told us was inside of x squared plus y squared equals 4. So that's a circle centered at the origin of radius 2. So this is the base of the solid. Okay, and this is the top of the solid. This is some capping surface. I think that is a cone of some sort. We'll take a look at it in a little while. Okay, so if you're going to iterate this double integral, that means start putting the limits on there. I'm going to choose my favorite order of integration, which is dy dx. So that means it's vertically simple. And so that means if I put my little man inside the region of integration, because this right here is the region R that this R is talking about. If I put my little man in there vertically, I'll notice that the top of his head is touching the top portion of the circle. So that's an upper limit for y. And his feet are touching the lower semicircle of, so that's the lower limit for y. Okay. Now x is going from a pure number to a pure number, because that's the outermost integral. So we can immediately iterate that outer integral going from -2 to +2. But the what do you do here? Do you put the circle, here's like the upper circle is going to be the limit for the upper limit of y, and then here is the lower semicircle here. So how do you do that? Well, you're going to need to solve your circle equation for y. So the circle equation was x squared plus y squared equals 4. And if you solve for y, you'll get plus or minus the square root of 4 minus x squared. Now, it turns out if you graph the positive square root, you'll get the upper semicircle. So that's going to be our upper limit for y. And then if you graph the negative square root of 4 minus x squared, that is the lower limit for y. So you're going to go negative square root of 4 minus x. So there, I have done my due diligence, and I've set up the double integral representing volume in rectangular coordinates. But this is going to be kind of hard to do. Like, I don't even want to try to integrate this, because I'd need trig sub and who knows what else. So we're going to convert to polar. And now, why is this a good candidate for converting to polar? Because the region of integration is a circle. The region of integration is a circle, or a portion of a circle, or some sort of polar sector like a rose curve or something like that. Perfect candidate for converting to polar coordinates. Okay? So the first thing I want to do is I want to notice that the radicand can be rewritten. You can factor out a negative from the last two terms. And then when you convert the radicand to polar, it's going to look like 16 minus r squared. So that's kind of nice. And if you look at the region here, R and theta are ranging from what to what? Well, R, remember, do not say R is going from -2 to 2. That's not okay. R is the kind of thing that blooms out from the pole. It starts here at 0 and then gets bigger and bigger and bigger and bigger until it's 2 units away from the pole. So R is going between 0 and 2. And because we're talking about the entire circle, theta is sweeping out an entire revolution, 0 to 2 pi. Now, the dy dx, which is the area element for rectangular coordinates, when you rewrite the area element for polar, remember we talked about this last time, be a pirate. So what do I mean? What do I put here for the area element for polar? Does anybody remember?
R dr d theta.
Very good. R dr d theta. So your R is going from 0 to 2, and your outermost integral is with respect to theta. So we got 0 to 2 pi, and now we're ready to integrate. And this is integrable. The inner integral that we're going to look at here involves the power rule and U substitution. So anytime you're using U sub, you need to tell me what the U and the du are. So U is the radicand, 16 minus r squared, and the derivative of 16 minus r squared with respect to U is -2r. And then don't forget to put your dr there. Now, good news and bad news. R and dr exist here in the integrand, which is great. So the only thing that my du is missing is a -2. So I need this -2 in there. So what I'm going to want to see you do is I want to see you put a -2 in there, provided you multiply the front of the integral by the reciprocal of -2, which is -1/2. And then I need you to do an intermediate step if you want full credit. So let me start copying stuff down here. This integral that we have in the middle, the innermost integral, I want to see you rewrite it as square root of u du. I want to see that intermediate step. Please. Now you still have the outermost integral with respect to theta, of course. And then this innermost integral, radicals are evil. Yeah. So I want to rewrite that with exponents. So that's really u to the half du, and then I want an intermediate step. Using the power rule, it's u to the half plus 1, divide out by a half plus 1. But that's the same as u to the 3/2 divide out by 3/2. But dividing by 3/2 is the same as multiplying by the reciprocal, which is 2/3. Okay, now be careful because you do not want to do the following. Do not evaluate 2/3 u to the 3/2 between 0 and 2. No, no, no. Why not? Because the 0 and 2 limits have to do with r, not what u is doing. So you have to be really careful because I've seen students do this where they accidentally forget to back substitute for u, and they start hitting in the limits right away, and it's like, ooh. And that kind of silly mistake is going to get you in a world of hurt, okay? So please back substitute your u, which was, what the heck was it for us? 16 minus r squared, and then we'll evaluate that between 0 and 2, okay? And I still have my outer integral. Okay, now you have to be careful here because a lot of times when people see the 0 for the limit, they go, oh yeah, I don't even have to worry about plugging in the 0 because everything always goes to 0. Not every time, and definitely not in this particular case. So be careful. I'm going to whip the 2/3 out in front just because it's just a multiple. So now what I have is I have 16 minus the upper limit squared to the 3/2 minus 16 minus the lower limit, which is 0, that whole thing to the 3/2. So you see how that's definitely not going to be 0 there. I'm going to reduce -1/2 times 2/3 to -1/3. Here we have 16 minus 4 to the 3 halves minus 16 to the 3 halves. Clean this up. What do you mean? Well, there's a few things that you can do. Let's do the easy one first. 16 to the 3 halves means the same thing as square root of 16 cubed, but that's the same as 4 cubed, but that's the same as 64. Ah, nice. Okay. Now this first term isn't as nice. It's 12 to the 3 halves, which really doesn't simplify much. But remember, it's the same as 12 cubed, the square root of that. So if you think of the square root of 12 cubed looking like the square root of 12 times, 12 times 12. This might help a little bit. And then you can clean this up even more. Let's see, that's a perfect square. And then 12 is 4 times 3. So this is looking like square root of 104 times square root of 4 times square root of 3. I'm doing this in slow motion, but there's quicker ways to do it. But this is really 12, square root of 4 is 2. And so this is looking like 24 square root of 3, which looks a little prettier. Okay, so what do we have? We have this yucky number, 24 square root of 3 minus 64. It's just a constant. And now we're still integrating because we still have to integrate with respect to theta. Okay, but a constant, the antiderivative of a constant with respect to theta is just going to be the constant. I'm going to pull the constant out here, times theta. And theta is going to go from 0 to 2 pi. And so our final answer is going to look like not that nice. This is the exact answer. Wow. Cubic units. And it is a positive number. Well, it looks negative. Well, yeah, it does look negative, but it turns out the number in between parentheses is negative. So it's a negative times a negative. It's a positive. You can punch this up in your calculator to get an approximate answer. And I get approximately 46.98, which is positive, cubic units. Woo! So let's recap this problem. What the heck? They asked us to set up a double integral in representing the volume of a solid where they gave us a capping surface and they told us about the base of the solid. Turns out it was really kind of crazy to have to evaluate that using rectangular coordinates, so we converted to polar, and then it turned out it was integrable. Yay, success. And then we had to do a bunch of U sub and work it all the way out. Okay, so that was a really crazy example. So one of the big things about that last example that I wanted you to see was that polar is really helpful because it comes and swoops in and saves the day when you have an integral that's just not integrable in an easy way using the rectangular coordinates. So polar is really a lovely thing. So I want you to be motivated to learn it because it's going to help you out a lot. So this next example is a little different from the previous examples for a couple of reasons, and we're going to see why in a moment. And again, I should have left myself tons more room. My goodness, I have to do that for myself next time. So what do we have here? We're trying to find the volume of a solid again. Okay. The base of the solid is given by an annular region, also known as a donut, and it's between two circles here in the xy plane. So x squared plus y squared equals 1 unit circle, and then x squared plus y squared equals 5. Be careful because the radius for x squared plus y squared equals 5 is the square root of 5, not 5. And that's a number that's a little bit bigger than 2, but not much. And so here's the base of the solid. Okay, and hopefully you get that if you had to set this up using rectangular coordinates, you probably have to cut this up into 4 separate double integrals because you would want to have one region here that you would treat, then another, oh, I don't even think that would work. I think this region here, then this region here, then there'd be 4 different regions. It'd be a mess. Much easier to do this in polar because of the nature of the region of integration. So this donut is the region R of integration. So when you go volume equals double W, double, and you put an R down below the double integrals, that R is your region of integration. And then you'll put your capping surface here in the integrand, and then you've got your area element here. So they gave us the capping surface. That's nice. Okay. But I don't even want to try to have this be in rectangular. I'm going to immediately go to polar. But first, look at our region R of integration. Let's figure out the range for theta and the range for R here. So the range for R, we have the radius starting at 1. And remember, R is the kind of thing that blooms outward. It starts here at 1, and then it gets larger and larger in that region until it hits the maximum it can get there, which is square root of 5. And since we're looking at the entire donut, we have an entire revolution, 0 to 2 pi for theta. Okay, so what does that mean? That means we can start iterating our double integral here. So we're going to have double, and then the area element is, for polar, R, dr d theta, be a pirate. And then theta is going from 0 to 2 pi, and then R is going from 1 to square root of 5. Now, we got to convert the x squared plus y to polar. Now, if this capping surface were x squared plus y squared instead, oh, that would be so much better, because x squared plus y squared is easy to convert to polar. Does anybody know what x squared plus y squared converts to polar?
R squared.
Yes, thank you, r squared. But this isn't that. Oh, did they forget the y? Maybe it's a typo. No typo. This is actually the capping surface. So we're going to go r squared cos squared theta. You're going to basically put in what the conversion formulas are. X is equal to r cos theta. And so that's getting squared. And then y is equal to r sine theta. Okay. Just for fun, let's go to our graphing utility here, and let's just find out what does that graph as. I'm just curious. I want to know what that capping surface looks like. Z equals x, whoops, I blew it, x squared plus y. What the heck does that? Whoa, stop spinning. Okay, so that looks like, whoa, kind of looks like it's a cylindrical surface. Kind of looks, well, sort of cylindrical anyway. Stop spinning. So that's the capping surface for this particular solid. And I didn't get the chance to see the capping surface for the other. So if we looked at the, I think we had, what did we have there? Square root. I think it was 16 minus x squared minus y squared. What did that look like? That was the previous problem's capping surface. Just for fun. Whoa, that's a kind of a cool capping surface. You can see how that's kind of nice. Of course, I like, yeah, that looks kind of pretty. Okay, nice. Okay, so just to taking a look at some of our capping surfaces. You don't have to do that, but it's kind of fun to always look to see, like, what does that capping surface look like? So that's the top of the solid. All right, so we converted the capping surface to polar here. So watch closely what's going to happen here with this problem and why it's different from previous problems, because it's going to hit us soon. And this is the kind of thing I put on quizzes and exams. So yeah, is the previous problem similar to what I put on quizzes and exams? I almost always can be counted on to put in some sort of use of on quizzes and exams. So this coming quiz, just be apprised that, yep, you're going to be doing a power rule use of somewhere in the quiz. Is it exactly this kind? Maybe, but maybe it's just similar. Okay, so back to the matter at hand. Now, folks, I'm supposed to integrate with respect to R right now. but you better not. Well, why not? It's supposed to integrate with respect to R, because this R from the area element needs to be distributed along the parentheses there before you integrate with respect to R. And that's important. If you forget to do that, the rest of the problem is going to be horrible. It's most likely be incorrect. So you're going to have R cubed cos squared theta plus R squared sine theta. Great. Now we're ready to integrate this with respect to R. Now keep in mind, we're keeping theta constant when we're integrating with respect to R. So the cos squared just looks like a constant multiple, and so does the sine theta. That just looks like a constant multiple also. So I'm just going to sort of put the cos squared off to the right, or to the left rather, and then take the antiderivative of R cubed, which is R to the 4th over 4. And you're going to evaluate that between the limits of 1 and square root of 5, but I'm going to just integrate the other term. The sine theta is just a constant multiple, and the antiderivative of R squared is R cubed over 3. So we're going to evaluate this antiderivative between the limits of 1 and square root of 5. Always remember to substitute your upper limit first, and we're substituting in place of the R's. Now the cos and the sine, they're just going to go along for the ride. So don't like erase them. I'm just going to copy down the cos squared, and then I've got square root of 5 to the 4th over 4 plus sine theta, sine theta, and then square root of 5 cubed over 3, yuck, minus, oh no, I'm running out of room. Yeah, I know, put parentheses, cos squared, and then I'm going to substitute the lower limit here, which is a 1. Oh boy. And then we're still going to have to go d theta. Yuck. Now, this is going to get kind of messy, but you want to think like a smart rat when you do this. If you can, try to combine like terms and do as much cleanup as you can before the last integral. So it turns out that square root of 5 to the 4th power is 25. And this is just 1/4. So if you combine the cos squared terms together, the coefficient is going to, I factor out the cos squared, I'm going to have, and also distribute this minus, don't forget. You're going to have 25/4 minus 1/4, but that's 24/4. But that reduces to a 6. Oh, good news. So we're really just going to have a 6 cos squared theta. Beautiful. Then what? Well, when you factor out the sine theta, it's not going to be as nice. You've got the square root of 5 cubed, which when you simplify it a little bit is 5 square root of 5 thirds, and then minus 1/3. And that's not easily simplified. So that's going to be just that number. That's about, you could put it over one denominator, make it look a little prettier. Okay, fine. So this is what we have so far. We have to now integrate with respect to theta. And this is where it's going to be key. This is where the whammy comes up. So I want you to look at cos squared. So let's talk about a Calc 2 review right now. And if you don't remember this, I'm doing you a favor by reviewing. Yay. What do you do with a cos squared? You don't use u sub on it. Like, don't go, oh, that's u squared. Because there's no du there. I don't see any factors of sine running around. What do? When you have a cos squared or a sine squared, and they're asking you to integrate, you have to use the power reduction formula. And if you forgot this, don't worry, we're here to remind you, because yes, it's going to be on this coming quiz, and yes, it's going to be on the midterm, and yes, it's going to be on the final. That's how much I'm into it. I'm warning you now. So the power reduction formula for cos squared is 1 plus cos of twice whatever the angle is, 2 theta all over 2. The power reduction formula for sine squared, and don't blow this because I'm not putting a typo here. It's 1 minus cos. Are you sure? Isn't that a sine? No, there's no typo here. Both of these have a cosine. No signs involved. There's a cos here, and yes, there's a cos here when you're using the power reduction formula on sine squared. Okay, I would copy this down somewhere, because if you don't do this power reduction formula correctly, I'm not really prone to giving partial credit. That's how I want you to do cos squared or sine squared. Now the other term with, the other term that we're integrating here that's got the sine, that guy is not squared. I was just putting the sine squared here just to remind you for the future. If you end up doing one of these polar coordinate thingies and you end up with a sine squared, please use this correct power reduction formula. So let's actually integrate this term first, since it doesn't have any need for a power reduction formula, and everybody knows what the antiderivative of sine is, right? Well, I hope we do. It's minus cos, okay? It's minus cos, and then you're gonna have that weird constant kind of go along for the ride, and you're gonna, of course, evaluate this between 0 and 2 pi. What do you think is going to happen when you evaluate this term between 0 and 2 pi? Does anybody have an idea? Isn't cos of 2 pi the same as cosine of 0?
Yeah.
So what's going to happen when you plug in the 2 pi and you're going to get something, and then you go minus this thing where you're plugging in a 0 and it's essentially the same thing.
Cos squared.
You see this whole thing will just go to 0?
Oh, yeah.
Because you're just doing it one whole full revolution. So it's not going to contribute anything. I mean, if you don't believe me, go do it in slow motion for yourself, okay? I encourage you to do that if you don't trust me. So I just claim it's one big fat 0. Well, does that mean the whole answer is 0? No. You're misunderstanding me. I did not say that. I'm not done with this problem yet. Hold on to your horses. I'm still having to do the 6 cos squared. Now that guy does not end up being a big old 0. So he's still over here, and we're still going to work on him. Oh yeah, so let's do this guy in slow motion here. First, you use the power reduction formula, which says that cosine squared can be rewritten as an equivalent identity for trigonometry here. Woohoo! Thanks, Clayton. I love that horse. And then I don't like fractions. So before I keep going, so I don't get screwed up, because, I don't like making silly mistakes, I pull out the half in advance just so I don't forget about him. And then I go ahead and integrate. So then this is a 3. Now the antiderivative of 1 with respect to theta is just theta. But when I'm anti-differentiating cos of 2 theta, u is 2 theta, du is 2 d theta, so I need a 2. So I need to put a 2 in here and then multiply the front. Now be careful, not the whole front. You don't want to affect this theta here. He doesn't need the half. It's only this last term that needs the half. So now I have a half cosine of u du. And yes, we'll do this guy between 0 and 2 pi in a moment. And then the antiderivative of cosine of u is sine of u, not negative, positive when you're taking the antiderivative. And then you're going to back substitute what was u, it was 2 theta. So my antiderivative complete with respect to theta is the 3 out in front here. And then I've got theta plus 1/2 sine of 2 theta. Now you can start substituting in your limits here. and then minus, and then when you plug in the 0, this will go to 0 because sine of 0 is 0. And then sine of 4 pi, I believe, is also going to give me a 0. So the only contributing term is the theta. And so my final answer is 3 times 2 pi, which is 6 pi. And we were doing a volume problem. So cubic units. Woohoo! Yikes. And we're done with that example. So why was this a really important example? A lot of things going on here. We had a donut for the region of integration, which you never want to try to do a donut using rectangular coordinates. Always convert. And we converted it. And then after we converted it, we ended up having to use a power reduction formula. It's a trigonometry identity in order to integrate. And that was kind of fun. And then we ended up completing the double integral. Okay, new example. Letter E, sketch a region of integration, convert to polar, and here's a double integral. Okay, so this one's a little bit different because we don't have to do the setup. They already set it up for us. Oh, thanks, guys. But here's the hard part. Sometimes when I do the setup for you and I say sketch the region of integration, that can be a little bit of an issue for some folks because they're not clear on the region of integration. So if you follow my little step-by-step procedure that I taught you in previous lectures to do the region of integration, you should be okay. So the outermost integral is with respect to y. So if you look at the limits 0 and 3, write down the equations y equals 0 and y equals -3. And you can graph those. Y equals 0 is a nice horizontal line that lives on top of the x-axis. And y equals -3 is another horizontal line that cuts through the y-axis at -3. Fine. Then the innermost integral has to do with x. So you're going to be graphing x equals 0 and x equals, negative square root of 9 minus y squared. Oh my goodness. Okay. X equals 0 is pretty easy because it's just the vertical line on top of the y-axis. But how the heck are you going to graph that? Because your graphing calculator only lets you graph functions of x, not functions of y. So there's two ways to do that. One way is to try to rewrite it and hope for the best. But I want to show you how to parameterize right now, even though we won't be doing a lot of parameterization of curves until about 2 weeks from now. Well, maybe a week and a half. Anyway, so how would you parameterize this and be able to use your graphing calculator in parametric mode to graph it? Well, remember, for functions of y, which is what this is, you let y equal t. And well, then what's x? Well, x is the opposite of the square root of 9 minus y squared. But if y is equal to t, then you just substitute. X will be negative square root of 9 minus t squared. Now, then you whip out your graphing calculator. Oops, come on, graphing calculator. Mine takes a while to come up. And then in parametric mode, you can graph it. So that's the cool thing about knowing parametric mode. It's really great. So let me just go to mode. Okay, I'm already in parametric mode. Fabulous. Go to y equals. Let's clear out any junk that we had from the last time we used the parametric mode. So I'm going to have x is equal to negative square root of 9 minus t squared. Okay. And then the y was just t. And then let's just check our window. Yeah, we could try doing that. It's not going to be the domain. Oh, check all my arguments. Okay, what happened is I tried to feed it values of t that were not okay. Hey, okay. So let's go to our window. Let's go T min 0 and T max 10. Let's see what happens now. No, still doesn't like me. Okay. Let's see what go to. Okay, I have to stop at 9 because if I put in a 10, I get a square root of a negative number. Wow, this thing is really picky. All right, let's see if it likes it now. Nope. Wait, what? What am I doing wrong?
Perfect. Question.
Okay, so I would like to just say that something is going on with my graphing calculator. Some people are having no problem with it, but I would like to, let's go ahead and just work with x equals negative square root of 9 minus y squared, okay? So that is the leftmost semicircle of a circle centered at the origin of radius 3. Pretty cool, huh? So what I want to look at is if you graph a leftmost semicircle, there it is. Now that is the graph of negative square root of 9 minus y squared. Now, here's the question. When you have all of these fences, look at all the 4 fences here, and this is where students kind of blow it. They shade in something that's not correct. What is my vegetable garden looking like? What is the portion that's bounded by all 4 of these graphs?
The lower half of the semicircle?
Very good. Very good. The left bottom quarter of the circle. We're over here in quadrant 3. That's important for you to get. That is important for you to get. So what of it? Well, down here. Okay. There is the region of integration. Wow, that, oops, sorry, that's the wrong, I'm graphing the wrong thing. Sorry, that's letter F. Save it for later. Okay, I'm up here. Okay, so now what? Well, that's kind of interesting. Let's talk about what the limits of r and theta would be for this little cute quarter of a circle. Theta is going from pi to 3 pi halves. Do you see why? Because it's starting here at pi, and then it ends up down here at 3 pi halves. Okay, be careful, because that's the range for theta. Now, please do not tell me that r is negative. R, remember, kind of starts blooming out here at the 0, and then it blooms out, bloom, bloom. So it goes from 0 to 3. It's important that you get that. So now, if I try to convert this to polar, because that's my next thing I'm going to try to do. So I'm going to try to convert this to polar. Okay, first up, I already know that my area element here isn't going to be dx dy anymore. It's going to be r dr d theta. X squared plus y squared converts to r squared, and then 4 plus x squared plus y squared converts to 4 plus r squared. Okay, and then we have agreed that r goes from 0 to 3, and theta goes from pi to 3 pi halves. Okay, and so you always get partial credit if you can do the conversion. Not whole bunches of points, but it's like, hey, you converted it. Congratulations. Now what? You're going to need to multiply the factors of r together there in the numerator to get a single factor of r. And this is where students lose it, because this is what we call an improper rational function. Why is it improper? It's an improper rational function when the degree of the numerator is greater than or equal to the degree of the polynomial in the denominator. And here, the degree of this polynomial in the numerator is 3, and the degree of the polynomial in the denominator is 2. So we definitely have an improper rational function. Well, what do you do? Well, you should have learned this in Calc 1. And if you took me for Calc 2, we went over this. I used to test you on this like every other quiz. It was on the final. Anybody remember? Does anybody remember polynomial long division? Sort of,
Probably,
kind of, maybe.
kind of.
You got to do it because you're not going to integrate that right now. Like, don't even go there. So what do you mean? How many times does r squared plus 4 go into the numerator of r cubed? Focus your eyeballs on the highest power terms. R squared times what gives you r cubed? Well, I think it's just r. And then you go r times r squared is r cubed, r times 4 is 4r, and then you subtract. R cubed minus r cubed is 0, and you have a 0 placeholder up here in the dividend, and 0 minus 4r is minus 4r. And you're done because this remainder is a polynomial of degree less than the divisor. And then here's the quotient. So when you write your answer, it has to be quotient plus remainder over divisor. So our innermost integral now needs to look like r plus negative 4r over r squared plus 4, like this. Okay, that's where we're at right now. Crazy, huh? So can we integrate this? Yes. Very, very carefully. The first term, easy peasy. The antiderivative of r with respect to r is simply r squared over 2. Plus, then how do we integrate this? Well, I'm going to pull the negative 4 out and look at what's inside the integrand there, r over r squared plus 4, and this is going to require the log rule. So with u sub, so you're going to tell me the u and the du, otherwise I don't give you full credit. So the u for, and by the way, the log rule says 1 over u du's integral is ln absolute value of u. That's the log rule. U is r squared plus 4. Du is 2r dr. Good news and bad news. R and dr are already in your integrand. That's good. So what are you missing? Well, I'm missing, and what I need is a 2. So I put a 2 in there, provided I multiply the front of that little integral by the reciprocal of 2, which is a half. And now this integral looks like negative 2, 1 over u du, which is going to translate to negative 2 ln absolute value of u. And please remember to back substitute your u, because it was r squared plus 4. So negative 2 ln absolute value of r squared plus 4. So what I have now is I have this first term, r squared over 2, which is good. And then I have the other term's antiderivative, the one involving a logarithm. And then we have to evaluate this between the limits of 0 and 3. That's not too hard. Be careful, because the 0, if you ignore it, you'll hurt, because that doesn't all go to 0. So the upper limit, do that one first. Oops, I'm going kind of fast here. And then minus, and then substituting the lower limit of 0. Be careful, because even though r squared over 2 will in fact go to 0, the rest of it won't. Because this logarithm, you're gonna have a minus minus here, which looks like it's going to be plus a 2 ln of 4 there. And then you also have a 9/2 minus 2 ln of 9 plus 4 is 13. That's kind of weird. And this is just one big old yucky number. This is just a number. Now I'm going to do a little bit of stuff here on the side. 2 ln 4 can be rewritten as ln of 4 squared. And then this here, you could rewrite it as minus ln of 13 squared. I'm condensing using some log properties. And then this can be condensed into ln of 4 squared over 13 squared, a single log, but that's ln of 16 over 169. Okay, and then you still have the 9/2. So what am I saying? This number 9/2 plus ln of 16 over 169 is just some constant that's sitting out in front of the last integral that we still have to integrate. And we'll finish it off. So the antiderivative of 1 with respect to theta is just theta. And you're going to evaluate the theta between the 3 pi halves and the pi there. And that's just going to give you pi halves. So our final answer is going to be this weird number. I know. I don't know. Weird number. That. Which is approximately 3.3657. And we don't know if this is representing a volume or not. So I'm not going to put cubic units because they didn't say that. And I mean, it could, but who knows? Okay. And that concludes that example. Okay, something not in your course reader that's good to address right now are portions of a circle, upper and lower semicircles, or right-hand side semicircle and left-hand side semicircle. Let's talk about that. Let's say you just have a generic circle centered at the origin, x squared plus y squared equals 4. Let's make it easy, okay? And I hope all of you know that that represents the entire circle centered at the origin of radius 2. Okay, fine. Now, it is not a function of x or a function of y, okay? Because it doesn't pass the vertical test or the horizontal line test, okay? Now, if you wanted to rewrite it as functions of x, you would solve it for y. And if you solve for y and you square root both sides, you know, anytime you do a square root of both sides of an equation, you end up having to do a plus or minus, okay? Now, what happens here? So this represents the whole entire circle for sure, but you have to graph two separate equations. You have to graph the positive square root of 4 minus x squared and the y equals negative square root of 4 minus x squared to look at the entire circle. So when you graph the positive square root of 4 minus x squared, you'll get the upper semicircle. If you graph y equals negative square root of 4 minus x squared, you'll get the lower semicircle, okay? And you can test this on your graphing calculator in case you don't believe it. So that's one way of looking at the circle. What's another way? Well, sometimes you might find yourself needing functions of y instead of functions of x. So in that case, solve the circle equation for x. So once again, you're going to have to take square root of both sides. And you'll get that x is equal to plus or minus the square root of 4 minus y squared. Now, this also represents the entire original circle, but to see the whole thing, you'll have to graph two separate graphs. So you'll first have to graph the equation x equals positive square root of 4 minus y squared. And then you'll have to graph x equals negative square root of 4 minus y squared. These are functions of y separately. Well, if you graph the x equals positive square root of 4 minus y squared, this one here, you will get the right-hand side semicircle. If you graph x equals negative square root of 4 minus y squared, you will get the left-hand side semicircle. Okay, not upper and lower this time. You'll get right and left. Okay, and then together that recreates the whole entire original circle. So I wanted to take this little side trip here to make it a very important point, because when you're doing polar, you have to know these little factoids here, the little factoids about breaking down a circle equation and rewriting it as either a function of x, like these two guys, or solving for x, you'll get functions of y. And as you know that's important. especially if you're switching the order of integration, okay? Okay, another example where your R is not going to be from a pure number to a pure number. And yes, I'm going to put one of these on quiz and an exam and so on. So you better know how to do it. Okay, so why the heck is this different? Okay, first up, they're asking us to shade in the region of integration. All right, outermost integral is with respect to y. So let's go ahead and graph the equations y equals 3 and y equals 0. Easy peasy. Those are just horizontal lines. Fine. And now we're going to graph x equals 0 and also x equals the square root of 3y minus y squared. And if you want to use your parametric mode, it should work. It's not working for me. But here, if you let y equal t and then x equal the square root of 3t minus t squared, it should work for you. X equals 0 is easy because it's just the vertical line on top of the y-axis. Now, if your parametric doesn't work, let me show you, because mine doesn't right now. What I'm going to do is I'm going to square both sides. Watch closely how I'm going to do this, because you may have seen this in your trig class. Okay. And then I'm going to move everything to one side and 0 on the other. And then I'm going to complete the square. Because I claim this is a circle equation, but the circle is not centered at the origin. So I need to add a special number there to make that a perfect square trinomial. And it's always b over 2 squared. So negative 3 over 2 squared is 9/4. So if I add 9/4, I know this is pretty weird. You'll get like that. Then you'll go, oh my goodness. And then this is a perfect square trinomial. Y minus 3 halves, the quantity squared equals 9/4. So that turns out to be a circle centered at 0, 3 halves with radius equal to 3 halves. Okay, fine. Well, that's kind of weird. You know, yeah, so in other words, like 0, 3 halves is like right there, and it's got a radius of 3 halves, so it's going to look like something like that. Is it the whole circle? No, it's not the whole circle. It's only the right half sides of the circle. So it's really that. Another way you can do this that you'll want to do, because you really have to figure out what R is doing, is take a look at the equation again. X equals the square root of 3 minus y squared. Once again, square both sides. Okay. And then go ahead and add y squared to both sides. And then take a look at that and convert to polar. Well, how do you convert that to polar? Well, x squared plus y squared is r squared. And then when you convert the right-hand side to polar, you'll replace y with r sine theta. And now you're going to do something that's usually illegal in math. You're going to divide both sides by a variable. Why is that usually illegal? Because that variable could be 0, and you don't want to divide anything by 0. But let's assume r isn't 0. And not only that, we pick up 0 in the final result. R is equal to 3 sine theta. So if you use your graphing calculator and graph r equals 3 sine theta, you should get a full circle like this. So you can try that. And I'm not going to try my graphing calculator again, because I don't even trust that thing right now. It's being a little bit grouchy with me, but I can certainly use my software here, and I can go r equals 3 sine, and I start typing in the word theta. It should give me a theta. And then notice it is a circle that isn't centered at the origin with a radius of 3 halves. Pretty cool. Woohoo! Success. So what is the point that I'm trying to make here? I'm getting somewhere with this. And why is this in my lecture notes? It's different from all the other types of problems here. Okay, because your region of integration bounded by all 4 of these equations is the right half semicircle of this circle that isn't centered at the origin. So the important part is when you start converting to polar coordinates, R is going to go from 0 to 3 sine theta. Now, what is theta going to be doing? Oh, that's the hard part. It turns out that theta is starting here at 0, and then it sweeps out to stop up here, but that's where theta is equal to pi halves. So your limits for theta here are 0 to pi halves. So when I convert this to polar, and then square root of x squared plus y squared is just r, and then the area element is r dr d theta, and then you want to multiply these r's together. That's not hard to get a single power of r. And now you can go ahead and integrate as usual. Well, this isn't going to be hard. This looks like it's going to be easy. Whoa, whoa, whoa. This is a hard problem. Hang on a minute. You'll see in 2 seconds. Well, the antiderivative is easy. It's r cubed over 3. Okay. Nothing hard there. I know, not yet. Then you're going to go, all right, let's go ahead and substitute in the limits. Well, nothing hard there. I don't see the problem. Oh, well, not yet. And 27/3 reduces to 9. Now here's the problem. When you were in Calc 2, you may have had this problem. How did you deal with sine cubed of theta? Not the power reduction formula. You first rewrote it as sine theta times sine squared. This is because the 3 is odd and positive, and you had to use these guidelines for powers of trig. And then you convert the remaining sines to cosines. And sine squared was not hard because it's 1 minus cos squared. And then distribute your sine. Anybody remember this from Calc 2? Sort of, kind of, maybe. Now the integral of sine is easy peasy. You're just like, oh, okay, that's just going to be minus cos. But then how do you integrate this here? You're going to use the power rule with u sub. Really? Yeah, you're going to go u is cos, and du is negative sine, d theta, and I'm going to take this minus and turn it into plus a negative, so that I could bring the negative in there. And there we already have negative sine theta d theta. So this actually looks like u squared du. Perfect. So the antiderivative of that is going to be u cubed over 3. And then don't forget to back substitute for u. What was it? And now you can go ahead and evaluate at the limits. But cosine of pi halves is a nice number. Anybody remember what it is?
0.
And cosine of 0 is a nice number. Anybody remember what that is?
1.
Okay, so this is going to end up being, after you distribute your negative and so on, your final answer is going to be 9 times 2/3, which is 18/3, which is 6. And there's our final answer for that problem. Woo, that was crazy. So a little bit of Calc 2 knowledge was required here. Powers of trig, you may have remembered, and then also having to convert an equation to polar. And that is an important concept. Okay, and you may have remembered doing that in your Calc 2 as well. That's a Calc 2 skill that they taught you at the very end of your Calc class. Okay, now let's do taller and shorter. Okay, so on your quiz, you may have noticed there was a problem where you had to find the volume where you had a capping surface and an underbelly. And I didn't do one of those for you in class, but they did have it in the homework. So let's talk about it now. Sometimes your bottom of your solid that you're trying to find the volume of is not the flat base there in the XY plane. Your solid might not only have sort of a curvy top, but it might have a curvy bottom as well. So it's going to be bounded below by some surface. So this is an example of that. And there's a picture of it. So there's this z equals x squared plus y squared is the red paraboloid. And then z equals 8 minus x squared minus y squared is the turquoise paraboloid. And where they both intersect is this solid right here, which looks kind of like an egg. They want us to find the volume of that egg. This is a little bit harder of a problem. Now, in the quiz problem, you didn't have to do this little extra step. You just basically what you did, and we're going to do that also, is your volume is going to be the taller surface or the minus the shorter surface. So we're going to need to do that. We're going to do the taller, this guy here, the top of the solid is the downward facing paraboloid, 8 minus x squared minus y squared. And we subtract from that the bottom surface, which was the upward facing paraboloid. And yes, you're going to have to distribute the negative here and do some cleanup. So you're going to have 8 minus x squared, then you're going to have another minus x squared minus y squared minus y squared. So you're really going to have to worry about your integrand being 8 minus 2x squared minus 2y squared. Oh my goodness, are you kidding me? No, I'm not. So before I do anything, I'm going to factor out a 2, and you'll see later why we're going to do that. Okay, so now what is the region of integration? Don't guess. If you look at this egg, I hope that you can appreciate that the widest part of the egg, the more fat part, is right there where the two surfaces intersect. And the region of integration is going to be the projection of this, of the shadow basically, that this egg makes on the XY plane if the sun were shining directly overhead. So if the sun is shining directly overhead, the shadow that the solid is going to make on the XY plane is basically going to be determined by the fattest part of this solid, which is right where the two surfaces intersect. So if you're going to figure out the region of integration down here for this particular solid, and so that you can even set up the double integral, is you will set these two surfaces equal to each other. So you're going to figure out the intersection. So when does z equal z is the question. Ha ha. So when does the upward facing paraboloid intersect the downward facing paraboloid? Now, you have to be careful here. You don't want to screw this up. I like to basically, I'm going to add x squared plus y and y squared to both sides of the equation. So on the left-hand side, I get 2x squared plus 2y squared. And the right-hand side, I get 8. And if I divide both sides of the equation by 2, I get x squared plus y squared equals 4. And folks, that is what's going on, the shadow or the projection, they call it, of the solid onto the XY plane. And this is the region R of integration. And I hope you can see it is a circle, so you better convert to polar because you don't want to be trying to do this thing in rectangular. So let's determine what the limits are for R and what the limits are for theta. Theta is going a full revolution, 0 to 2 pi, and R is blooming from the pole 0 to a 2. Okay, and then the integrand, which is 8 minus 2 times the quantity x squared plus y squared, you'll replace the x squared plus y squared with r squared. So really what this ends up looking like is 8 minus 2r squared, r dr d theta. Please don't forget that. And also remember to distribute your r before you try integrating with respect to r. Otherwise, you'll end up in trouble. And I'm doing this very quickly, obviously. So then I'll get an antiderivative of 4r squared minus 1/2 r to the 4th, and evaluate that between the limits of 0 and 2. This just ends up being a nice number. I think it ends up being 8. and then you'll just pull the 8 out in front. It's a multiple, and the antiderivative of 1 with respect to theta is theta, and your final answer is 8 times 2 pi, which is 16 pi cubic units, of course, because this is representing the volume of a solid. That's that weird egg. And that concludes that example. So that example was a little bit different flavor because you had a capping surface as well as an underbelly surface. And just like the analog in Calc 1 is when you were doing the area between curves, you were supposed to do the taller curve minus the shorter curve. This is the analog to that. The taller surface minus the shorter surface. Now let's use polar coordinates to find area. So before we start, let me just say that you know how to use a double integral in rectangular coordinates to represent area, because area is simply a double integral over your region where you have a 1 as the integrand. Remember this? That's how you tell that the double integral is representing an area, if there's a 1 as your integrand. Well, it's somewhat similar here in the world of polar. Let's talk about the Calc 2 review. When you took Calc 2, they actually went over how to find the area of a polar sector. Now, maybe you forgot, but this is a review. The formula was an integral from some angle alpha to another angle beta, and it was 1/2 f of theta squared d theta. And the only caveat where r was f of theta, but r cannot go both positive and negative on your interval. If that happened, you had to figure out where it was only all positive or only all negative. And that's still going to be true for us. Otherwise, you might end up with weird areas like 0. You're going to go, wait, what? The area is not 0, for God's sakes. And that's how you'll know it might have screwed up, because your R end up going positive and negative on that same interval. So you might have to break it up a little bit. Okay. Now, what's the Calc 3 method? It's going to be a double integral. You'll still have your angle going from some alpha to beta. And then here, you'll have a lower, like G1 of theta, and then the taller, and then the area element is R dr d theta. Now, if your lower limit, G1 of theta, is equal to 0, this will agree with your calculus 2 formula. Really? Yeah. So like if you let it be a 0 here, let's just do it for fun. And let's make this, so let's have this be R equals 0, and let's have this be R equals f of theta for your upper limit, just so you can see what's going to happen here. If I integrate R with respect to R, this antiderivative will be R squared over 2. And then when you substitute that upper limit, you get the half f theta squared. So it's the same as your Calc 2 formula. Okay? So we're going to do one example, and then you can have fun with that on your homework. And of course, I have my pirate text messaging. R. Yeah. So we're going to use a double integral to find the area enclosed by the graph of 3 cos 3 theta. Okay, so if you go to your graphing calculator and you get into parametric mode, you're going to see that if you graph 3 cos 3 theta, and your window can be 0 to 2 pi. So this theta max here, you can try 2 pi. And then when you graph it, you should get a rose curve. And this particular rose curve has 3 petals. Now, it turns out that R goes positive and negative on this rose curve. And if you don't believe me, I hope you remember that since R is equal to 3 cos 3 theta, cosine is a kind of function that goes positive and negative on an interval. Yeah. So you need to find an interval where it's staying either all positive or all negative. Well, how do you do that? Well, one thing I can tell you is that as this rose curve gets sketched out on this polar graph here, it keeps hitting the pole. You see where it hits the pole? Pole is essentially the same as the origin in polar coordinates. And that's where R is 0. Well, why do you care about that? Well, let's solve the equation and find out when R hits 0, because that will give us some insight into one petal. And we'll find out the interval that theta sketches out with one petal. And then and since there are 3 symmetrical petals for this particular curve, we'll multiply the area of one petal by 3 to get the final answer. So that's sort of our strategy here, okay? So you're gonna have to do a little bit of trig. So you may not like this. So the question is, when does R hit the pole? When does it hit 0? When does 3 cos 3 theta hit 0? Well, first I'll divide both sides by 3, and 0 divided by 3 is still 0. Fine. Now you're going to take cos inverse of both sides of this trig equation, because you're trying to solve for theta. And cos of cos inverse of some angle is the angle. Cos inverse of 0. This is a little bit interesting. Please don't say 0, because that's not quite right. What is the angle whose cosine value is 0?
Pi halves.
Yep. Correct. And there's another one. How about negative pi halves? How about 3 pi halves? All of these are true. So I could have like 3 answers. Okay, I'm going to go with 3 answers. What the hell? If I multiply both sides of the equation by 1/3, my theta will be either pi 6, negative pi 6, 3 pi 6, but that reduces to pi halves. And you could have had negative 3 pi halves here, and that would have been something else also. Okay, negative pi halves. So what is it? What's happening here? If you look at the interval when theta goes between negative pi 6 and positive pi 6, cosine stays positive the whole time on this interval. And you can check me if you don't believe it. You can look at the graph of cosine, or you can look at the unit circle and go, yeah, cosine is positive. And then if you go over here to your window and you graph only when theta goes between negative pi 6 and positive pi 6, you'll see that you graph the petal that's sitting on top of the x-axis, if you will. Okay, let's just find the area of one petal, and then we'll use the symmetry of this flower and multiply by 3 to get the area of all 3 petals. Okay, that's the plan. So let's take a look at that. So what am I saying? I'm saying that this double integral that you're going to use is going to be the integral where theta goes from negative pi 6 to positive pi 6. Woo! There we go. And then R goes from 0 to 3 cos 3 theta, and then your integrand is going to be R drd theta. And this represents the area of one petal. Okay, so let's go ahead and continue with this, except of course I ran out of room. Geez, what else is new? I just never have enough room ever. Okay. So what's going to happen here is when I integrate R with respect to R, I get R squared over 2. And then I'm going to end up squaring this 3 cos 3 theta. Okay. And that's going to give me, oh my goodness, 9/2 cos squared of 3 theta. And the 9/2 is just a constant multiple, and you can pull it out in front. But then you have to worry about the power reduction formula. That comes next. Why? Because otherwise you're not going to be able to integrate a cosine squared. Now you have to be careful because you have to double the angle that you're working with. And so 2 times 3 theta is 6 theta, okay, over 2. And then I don't like fractions, so I'm going to pull the half out. And I'm going to integrate 1 plus cos of 6 theta with respect to theta. So the antiderivative is going to end up being theta plus 1/6 of sine of 6 theta. Oops. And remember, my limits for theta were negative pi 6 to positive pi 6. I know. So you're going to go pi 6 plus 1/6 sine of 6 times pi 6 minus pi 6 plus 1/6 sine of 6 times negative pi 6. A lot of braces going on. Now, 6 times pi 6 reduces to pi, and sine of pi is 0. So this term goes away. Over here, the 6's also cancel, and sine of negative pi is 0. So this term goes away. So the only term that is contributing is the theta, and don't forget to do a minus minus, which is a plus. You have 9/4 pi 6 plus another pi 6. So that's 9/4 times 2 pi 6. And then after reducing everything, I get 3 pi 4. But remember, that's one petal. So what am I going to have to do that is to get the area of the whole flower? Since this had 3 petals, and be careful because other curves in your homework may have different number of petals. This one had 3 petals, so 3 times 3 pi 4 is 9 pi 4 square units. And there's your area of the rose curve. Yay, success. Okay, I'm going to do one little planar lamina, and so I'm going to do the definition. I'll do one example. We'll do another example next time. So what is finding mass? And if you've taken physics, you know a little bit about mass, okay? But we're not finding mass of solids like most physicists do. This is going to be kind of weird. We're going to find the mass of a thin film, a planar lamina, something in 2D. Here's a planar lamina right there. And this one's constant density, okay? So the mass that we're going to be dealing with for this particular little section is going to be whatever your density is of your lamina times the area of your lamina, okay? So if you have a constant density, and they use the Greek letter rho, I don't know why they use a rho for density, but they do. Some use R, but if you have a constant density, like the density is 3 or something like that, then the mass would equal the double integral, and you would just have the constant there, and then you're integrating over that region. You're trying to find the mass of, okay? Now, what if your lamina doesn't have constant density? What if it's got some sort of variable density? Maybe it's thicker over in this corner, and then it's thin, and then maybe it's thicker over here. I mean, who knows? Okay. Well, the idea is you may have a density function rho that's variable. So it may be given by a function of 2 variables, rho of x, y. So if rho is a function and it's variable, then your mass, which we'll call m, is going to be your double integral, and you're going to put your row of xy, that's going to be a function of x and y, in your integrand. Now, folks, this kind of looks like a volume double integral. And if you're thinking, gee, this looks exactly the same as one of those double integrals that represent volume, except the f of xy represents a capping surface. And I'm going to tell you exactly right. It is looking exactly the same as a double integral representing volume. Yes, 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 except this is representing the mass of a planar lamina. And you better get a positive result, just like you should when you do volume. Okay, so let's just do one example. Let's say you want to find the mass of a triangular lamina with vertices at 0, 0. There it is, 0, 3, right there. And 2, 3. Ooh, 2, 3, looks like it's right there. Okay, let's connect the dots. There is the region of integration, people. That is the region R of integration. It's a triangle, and you're trying to find the mass of that cute little triangle when the density is variable. And they're giving you the density function right there. You're like, thank you. So your mass is going to be the double integral over this region. And you're just going to put the density function right here in the integrand. And, and then you're going to integrate over this region. Now, before I iterate this integral, you're going to have to do a little bit of work. This diagonal line here, you need to figure out the equation for that diagonal line, okay? Now, 2 points determine a line, so you know that the slope of the line is the rise over the run, and so that's the difference of the y coordinates divided by the difference of the x coordinates. So it looks like the slope is 3/2, and you already see that the y-intercept is 0, so the line is going to have the equation 3/2 x. And that's good to know. So if you're going to set up this double integral and choose my personal favorite order of integration, which is dy dx, now we can iterate the integral. So what is x doing on this triangle? Well, it's going from a low of 0, and the biggest that x gets is a 2. Now what's y doing? Well, if you put your little man in there, and this gets a little dicey here. I'm going to try to put my little man in there. Remember, he's got to be vertical. There he is. The top of his head is on the top of that horizontal line of the triangle. But that horizontal line just has the equation y equals 3. So the upper limit for this region for y is 3. And then the lower limit where the little man's feet are is on the diagonal line, which has the equation 3/2 x. Okay? Now, I'm going to switch the order of integration because I claim it will be easier. It'll be cleaner if you integrate this. And I'm not kidding. So if I flip this, I still have the variable density function. If I flip this to dx dy, what would be the limits? Now, y is the outermost integral. So y is going from a pure number to a pure number there, which is 0 to 3. What's x doing? Well, remember, dx dy is the horizontally simple choice for integration. So you're going to have to put your little man in there sideways. Sideways. It's kind of hard. Well, his head is touching the diagonal line. That's the upper limit for x. And then his feet are going to be touching the y-axis. That's going to be easier. Let's do that. That's x equals 0. And here you're going to have to worry about the diagonal line. But you don't want to put 3/2 x, because you don't want the variable of integration, which is x, to match one of the limits. So you need to solve the y equals 3/2 x for x. And that's easy because you're just going to multiply both sides by the reciprocal of 3/2, which is 2/3 y. So if you put a 2/3 y in there, this will be a lot more easy to integrate. I'll let you integrate the rest of this. This isn't that hard to integrate. Your final answer is 10. And mass in physics is unitless. So there's no units. This is, mass per area, essentially. Or your density function is mass per area. But your mass is just sort of, there you have it. Okay. And that concludes today's lecture.